Alrighty, so some molecules have more than one valid Lewis structure. So when I say valid, I mean the best Lewis structure. There's more than one that are equivalent that can all be considered the best Lewis structure based on formal charge and electronegativity. Sometimes we have more than one best Lewis structure. So when we have two or more valid best Lewis structures that differ only in the arrangement of electrons, they are called resonance structures. So when I say only the arrangement of electrons, that means the atoms are in the same order and everything. So this if we think back to our cyanate ion here, we had this. So even if we had the same bonding scenario, where we had carbon triple bonded to nitrogen, this isn't quite the same concept, but we had carbon triple bonded to nitrogen, and then if we put oxygen on the other side, that is not a resonance structure because now nitrogen is the central atom instead. If the central atom changes, then it's not the same conductivity. So it doesn't count as a resonance structure. When we have resonance structures, they're like this, like ozone down here. So we have the same atoms in the same places, we just change where we have double bonds. So the actual electron arrangement for some molecules or ions is actually a combination of the resonance structures. So let's look at ozone here. The two resonance structures for ozone suggest that the oxygen bonds in the molecule are not actually single bonds or double bonds, but something in between. So what does that mean? So we can draw these two resonance structures for ozone. So I'm just going to do the formal charges for this one over here. So this oxygen has 6 valence electrons minus 6 non-bonding electrons minus 1 bond gives it a -1 charge. And this one, we have 6 minus 2 non-bonding electrons minus 3 bonds gives us a +1. And this one's actually going to be 0 because we need it to add up to 0 because ozone is a neutral molecule. Okay, over here we've got 0 and the same kind of connectivity. So this one has the +1 and this one has the -1. So we've got the same setup. These are both valid Lewis structures. They're all oxygen atoms, so we can't really decide which one should have a positive or a negative charge. It's fine. So because these are both valid, both the best Lewis structure for ozone, but they're not the same. I mean, if you like turn your head upside down, one becomes the other one, but that's not what we're talking about here. So if we label these individual oxygen atoms as A, B, and C, they're not the same. So in this case, A, B, C. So in this case, A has the formal charge of 0, B has the formal charge of +1, C has the formal charge of -1. If those are the same labels over here, now A has the formal charge of -1, B has the formal charge of +1, and C has the formal charge of 0. So if we label them, we can see they're not actually the same. Anyway, what does that mean for us? So I'm going to erase these labels and things so that I can write again. So that means that both of these structures are the best. So we want a combination of those resonance structures. We want something in between single and double bonds. So the best way to think about this would be, this is the way I like to think about it at least, is we don't have a full double bond. We have like 1.5 bonds. Between each. So it's not a single bond, it's not a double bond, it's like 1.5 bonds. Because what we can see experimentally is that the bond lengths are the same. So we would think that the double bond would be shorter than the single bond, so we would see different bond lengths between the two oxygen atoms. But we don't. We see the same bond length between all of the oxygen atoms. So that tells us that those electrons are kind of hanging out across the whole molecule. We've got, I'd call them 1.5 bonds between each oxygen atom. And that's what we see. We see that the bond length is somewhere between single bond and double bond length. So let's talk about that a little bit more. Compounds with resonance structures don't really have single, double, or triple bonds. If we wanted to describe the bond order, the bond length, and the bond energy, like we did in the previous set of lecture videos, then the number of resonance structures and bonding pairs need to be taken into account. So you guys don't need to do this in your textbook, but I think it's cool to look at, so I'm going to show you anyway. So these are 3 different structures for the nitrate ion, NO3-. And they are all equivalent. We're just changing where the double bond is. So we're not changing the formal charge on nitrogen, we're just changing the formal charge on the 3 oxygens. So they're all best Lewis structures for the nitrate ion. But again, if we labeled the oxygens, we would see that they are different structures. Anyway, so to calculate the bond order, which we didn't really do before, before we just had bond order was 1 for single bonds, 2 for double bonds, 3 for triple bonds. But now we're going to calculate the bond order because it's not going to be 1, 2, or 3. It's going to be somewhere in between. So we take the total number of nitrogen-oxygen bonding pairs. So we look at the bonds. There are 4 bonds between nitrogen and the oxygen atoms. So those 4 bonds are 4 bonding pairs, and then we divide by the number of locations. So the number of locations are like our oxygen A, B, and C. So there's 3 different places where we put those 4 bonds. So sometimes we put the 2 bonds to oxygen B. Sometimes we put the 2 bonds to oxygen A. Sometimes we put the 2 bonds to oxygen C. So there's 3 places, A, B, and C. So it's 4 divided by 3 gives us a bond order of 1.33. So somewhere in between a single and a double bond. And we can see that if we actually measure the bond lengths. So a nitrogen-oxygen single bond has a bond length of 136 picometers. The nitrate ion, its nitrogen-oxygen bonds have a bond length of 124 picometers. And a double bond between nitrogen and oxygen has a bond length of 115 picometers. So, like we expected from this bond order, we are right in the middle of those, well, okay, not right in the middle. We're between those 2 bond lengths. So we're not at a single bond and we're not at a double bond. We're somewhere in between. Alrighty. Resonance structures show up in organic chemistry too, so you're going to see a lot of them if you continue on to organic chemistry. And some of benzene's unique properties are related to its resonance. So this is benzene. Again, you didn't need to memorize that, but this is benzene. In this case, so if I numbered these carbon atoms, 1, 2, 3, I can't write this small with my pen, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. So in this left structure, we've got a double bond between 1 and 6, 2 and 3, and 5 and 4. If those are the same ones over here, 1, 2, 3, 4, 5, 6, now we've got the double bond between 1 and 2, 3 and 4, and 5 and 6. So our double bonds have all shifted over. So this is a resonance structure. These 2 are equivalent resonance structures for benzene. Neither one is better. So the actual structure is kind of somewhere in between. It's a combination of both resonance structures. And we can see that based on bond lengths again. So a normal carbon-carbon single bond is 154 picometers long. The benzene carbon-carbon bonds are 140 picometers long. And a typical carbon-carbon double bond is 133 picometers long. So once again, we're somewhere in the middle. So the bond length takes into consideration the fact that we don't really have all single bonds, but we don't have all double bonds. We have half everywhere. So like 1.5 bonds, 1.5 bond lengths. So the resonance structures of, or the resonance is what we call it, of benzene gives it some of its unique properties. And I'm not going to talk about those, but you can learn all about them in organic chemistry. And just another note, Nick and I told you about this a little bit before. Chemists get kind of lazy sometimes, and we stop drawing the hydrogens in our bigger organic molecules. So we only draw the carbon-carbon bonds, and we draw lots and lots of hexagons. And I mentioned this at one point, might have been slightly after class. We talk about some more advanced things after class sometimes, where the resonance of benzene causes us to draw benzene as a hexagon with a circle in the middle sometimes. So that's another way you might see people draw benzene molecules. Alrighty, cool. So let's finish up with some exceptions to the octet rule. I've been mentioning these throughout, but we're saving like the big summary of exceptions to the octet rule for the end here. So there are 3 different types of exceptions. 1, the central atom has fewer than 8 electrons due to a shortage of electrons. I put hydrogen as an example, even though it's not a central atom. Just one of the atoms in the molecule has fewer than 8 electrons due to a shortage of electrons. We've seen that with hydrogen. What we'll see on the next slide is that we also see it with boron and beryllium. So boron trifluoride, for example, or boron trichloride, I think we saw on a previous slide. Boron actually is happy to have only 3 bonds around it. It's happy to have 6 electrons. So 3 bonds equals 6 electrons around it and not 8. So boron doesn't like to follow the octet rule. And we saw a little bit of why when we learned about formal charges, because boron, when we had that structure for boron with chlorine, and we tried to give boron a full octet by taking one of the lone pairs from chlorine and putting it on bromine, or putting it in a bond, I should say. When we did that, we found out that we had a positive charge on this chlorine, and that was bad. So that's part of it. That's part of why. But we'll see a little bit more on the next slide. So boron is one of these examples. What's our next exception? The other exception is that the central atom has fewer than 8 electrons because it has an odd number of electrons. And the example here is nitrogen. Nitrogen has 5 valence electrons. So when we put it in molecules, so all of the things that we've seen with nitrogen so far, really, we've seen the cyanide ion and the cyanate ion, and those were all negative ions. So those all had an extra electron from the charge, which helped us out because nitrogen had 5 electrons. But when we added that one in, we got an even number. When we have an odd number of electrons, we don't get so lucky. So for example, if we look at the nitrogen monoxide, nitrogen has 5 electrons, oxygen has 6, so there would be 11, there'd be 11 electrons in this molecule. So we'd have one little lone electron on nitrogen. If I put that lone pair into a triple bond, or that lone pair into a triple bond, 1, 2, 3, 4, 5. Sorry about that. I lost count of how many electrons I should have on my molecule. We need 11. So right now we've got 1, 2, 3, 4, 5, 6. Sorry, what am I doing? 1, 2, 3, 4 lone electrons, 2 lone pairs on oxygen, and we've got 2 bonds. So that is 8 electrons. So we need 3 more. So we can have a lone pair over here on nitrogen, but that one extra is just going to be hanging out. So there's this option for a resonance structure. It doesn't really matter what the resonance structures are, what the best Lewis structure is here. Either way, we're going to have this one electron hanging out, and that makes this a molecule. That makes this molecule called a radical. So we'll talk about that on a couple slides from now. And finally, the last exception is when a central atom has more than 8 electrons. So that's called an expanded octet. We'll get to that in a bit, but an example of that is SF4, for example. So sulfur has 6 valence electrons. There's 4 fluorines, which have 7, so that's 28. So we want 34 electrons. So if I draw my Lewis structure, that's my skeletal structure. Now I put on my electrons. Ran out of space a little bit there, but I've got 3 lone pairs on each fluorine, and there's 4 fluorines, so that is 12 lone pairs on each fluorine, or 12 lone pairs in general. So 12 lone pairs is 24, and we've got 4 bonds, so that's 8 more, so that gets us to 32, but we still have 2 electrons. And where are those going to go? They're going to go on sulfur. So sulfur is going to actually have more than 8 electrons. And we'll see that in a little bit here too. Alrighty, so first of all, our first exception is these incomplete octets. Some elements, notably hydrogen, beryllium, and boron, often have fewer than 8 electrons in their Lewis structures due to their electron configurations. So beryllium is in group 2. So beryllium, if we draw our Lewis dot symbol, it's got 2 unpaired electrons. It's got 2 valence electrons. So it only wants to contribute those 2 electrons to bonds. So it'll make 2 bonds, like beryllium hydride. But then we wouldn't have anywhere else to get those electrons from. So because beryllium only has 2 valence electrons, it only makes 2 bonds. And it doesn't usually get lone pairs donated to it from anywhere else. So beryllium and hydrogen are 2 of our exceptions. And then boron, we're going to talk about a little bit more here. So boron, if we look at boron trifluoride, I drew boron trichloride for you, but if we look at boron trifluoride, it's the same concept. Boron has 3 bonds. So boron, if we draw its Lewis dot symbol, pretend those are dots, it has 3 electrons. So just like beryllium, it doesn't actually want to make 4 bonds. It doesn't want to have 8 electrons. It's happy with 6 electrons around it because it only needs to make 3 bonds with its 3 valence electrons. So when we do that, then we have boron with only 6 electrons, breaking our octet rule. But if we throw in ammonia, the ammonia molecule is NH3, where nitrogen has a lone pair. So now we've got a boron that doesn't have a full octet, and we've got nitrogen with a lone pair hanging out. when we combine them, they form what's called a coordinate covalent bond, or a dative bond. This means that the nitrogen atom contributes both electrons to the bond. It takes this lone pair and makes a bond between itself and boron. So both of the electrons in this bond came from nitrogen, came from ammonia. So that's what's the difference between this and a normal covalent bond. They aren't sharing electrons that they each contributed. They're sharing electrons that came purely from the nitrogen in this case. And so in addition to having a special name for this, the coordinate covalent bond, there's also a special designation for these two interacting molecules. So the electron donor, which was NH3, it donated its lone pair to boron trifluoride. The electron donor is called a Lewis base, and the electron acceptor, so boron trifluoride, didn't have 8 electrons, and it got 2 from nitrogen, so it's an acceptor. The electron acceptor is called a Lewis acid. So we talked about acids and bases a little bit before, but this is a new version of acids and bases. There's a few different definitions of acids and bases, and you guys don't need to know them now, but this is one example of a Lewis acid and a Lewis base. And this comes from the fact that boron has an incomplete octet, which makes it very reactive. It is looking for electrons, but not from itself. It's looking for electrons from other molecules. Alrighty. Our other exception to the octet rule was free radicals. So these are compounds with one unpaired electron or more, but mainly unpaired electrons. So free radicals are also considered electron deficient compounds. So electron deficient compounds is one term for compounds where one of the atoms has an incomplete octet, other than hydrogen. Hydrogen is fine. But those boron and beryllium molecules are considered electron deficient. But free radicals are also considered electron deficient because there's one little electron hanging out and it wants to make a friend. It wants to be paired up. So it's electron deficient. It's looking for more. Nitrogen dioxide is a free radical compound because it's an odd electron molecule with 17 valence electrons. So nitrogen dioxide is NO2. So nitrogen has 5 valence electrons, and oxygen has 6, so there's 12 from the 2 oxygens. So that's what gets us to 17. And this is a neutral molecule, so we don't have a charge on our ion to take care of the uneven or the odd number of electrons. So this molecule has an odd number of electrons. That one unpaired electron hangs out on nitrogen like that, and that's what we call a free radical. And free radicals are highly reactive because of the unpaired electrons. So, for example, nitrogen dioxide reacting with itself, it forms this nice little compound so that it has all paired electrons, so that those two can just be combined into a single bond. So free radicals are highly reactive species. You might have heard of free radicals before because free radicals in the body are pretty bad because they're highly reactive. So if you ever drink or eat anything that's an antioxidant, that's actually to get rid of some oxygen radicals that are formed by the body. So unfortunately, the body forms some radicals, even though they're bad for the body. So if you have antioxidants in your system, that will help take care of those oxygen-based radicals or reactive oxygen species that exist in the body. And finally, the last exception to the octet rule is elements with expanded octets. So an element with an expanded octet will have more than 8 electrons. Often it'll have 10 electrons or 12 even in its Lewis structures. So what elements can do this? So the elements in the third period and below can be exceptions to the octet rule. So phosphorus and sulfur are big ones that you'll see a lot. Sometimes chlorine and bromine you'll see as well, or iodine. Those are fairly common expanded octets. So anything below, anything in period 3 and below, anything can be have an expanded octet. And that's because they are big. So we're going further down the periodic table. So we're getting more electron shells. So we're increasing our atomic radius. And once we're in period 3 and below, at least in the p block, in period 3 and below, we've got d orbitals. So the d orbitals that are in these atoms are empty and they can be used for bonding as well. So we're not really going to talk about bonding in transition metals or anything, but these elements in the p block in period 3 and below have empty d orbitals that they can use for bonding of electrons. So that's where we'll see these exceptions, and that's why we'll see these exceptions. So what can we also say about this? So sometimes you'll have 2 different structures. So you could have this structure of the SO4 molecule. So SO4, or not molecule, sorry, the sulfate ion, SO4 2 minus, the sulfate ion. You could see this one where sulfur obeys the octet rule. Or you could see this version with the expanded octet, where we're not following the octet rule. So how do we decide which one is better? In my opinion, we'd go with this one. But your book says that some people like the other one for different reasons, maybe because of its reactivity. But I prefer this one on the right because look at these formal charges. So formal charges, we've got a -1 on this oxygen, a -1 on this oxygen, which adds up to our total charge on our ion, which is -2. So that's fine, those are pretty small. But in this version, where we don't have an expanded octet, sulfur has a +2 charge, and all of our oxygens have -1 charges. So -1 for 4 oxygens plus +2 gets us this ion charge, which is correct. So this is a valid Lewis structure, but because of the formal charges, I don't like this one. I prefer this one for sure. That's what I would expect if I asked you to draw it. I would expect you to minimize the formal charges, even if it meant expanding the octet of sulfur. Okay, cool. All right, and then this is just a little summary for you guys. So when we're drawing Lewis structures, we want to follow the octet rule and not expand our octets unless it's necessary. So it could be necessary when we're predicting the best resonance structure with formal charges. So if we want to minimize our formal charges, which doesn't mean get them as small as possible, it means get them as close to 0 as possible. My students last semester had some trouble with that. When I said the term minimize, they thought that they should get it as negative as possible, which is not true. We want resonance structures with formal charges, all the formal charges individually, to be as close to 0 as possible. Okay, and then if we have all these different formal charges and we're in, our central atom is in period 3 or below, we can expand the octet to get the formal charges closer to 0. And one last note for you guys, your book mentions this a little bit, but formal charges are not measurable on atoms. They're kind of just made up for us to be able to pick the best Lewis structure. And by picking the best Lewis structure, we're also picking the Lewis structure that matches up with experimental data. So sometimes we make up some things to make things make sense. So formal charges are not actually measurable on the atoms, but if we use modeling programs, we can calculate more accurate partial charges. So we don't have these full formal charges. We actually have partial charges on pretty much everything, even if it's really close to a +1 or a +2 or -1 or -2. It's probably not exactly that. So modeling programs can give us more accurate partial charges. And this is what those look like. So these were modeled in a modeling program like WebMO, which you guys don't need to worry about. But some scientists use these modeling programs so that they can test properties of different atoms and molecules without doing the expensive or dangerous or whatever experiments. They can do all of their experiments on the computer. So this is what that looks like. So this is from like WebMO or something. And red indicates a positive partial charge. Yellow indicates a negative partial charge. So we've got negative partial charges on our oxygens in carbon dioxide. We've got negative partial charges on our cyanate ion. So this is actually not the structure for the cyanate ion that we said was the best one. So this one has a more negative charge on nitrogen, which is not good. So this is actually not the best Lewis structure. So I'm going to ignore that one. But let's focus on carbon dioxide. So for carbon dioxide, we've got a partial positive charge on carbon and partial negative charges that are equal on our two oxygens. And that kind of makes sense because an oxygen is the more electronegative atom. So that's where the electrons would hang out, making it more negative, having it a more negative partial charge. In carbon, when the electrons are away, we'll get a more positive partial charge. And another thing to note here is that the charges on the oxygens are equal, and that comes from our nice symmetric Lewis structure that we drew for carbon dioxide. Alrighty, that's it. I'll see you guys tomorrow.